Thermodynamics 1, Thermochemistry, Quantifying Heat. In this tutorial, we will be looking at heat, temperature, and thermal equilibrium, heat capacity, specific heat capacity, and molar heat capacity, specific and molar heat capacity example problems. Heat and temperature. Definition of heat. Heat is the exchange of thermal energy between a system and its surroundings caused by a difference in temperature. Temperature. Temperature is a measure of the thermal energy within a sample of matter. Temperature is also defined as the measure of the average kinetic energy of the particles that make up a substance. Thermal energy always flows from matter at a higher temperature to matter at lower temperatures. Thermal equilibrium. The net transfer of thermal energy stops when two objects reach the same temperature. Two objects at the same temperature are said to have reached thermal equilibrium. So if I have an object at 100 degrees Celsius and I have another object at 0 degrees Celsius, energy is going to transfer from the hotter object at 100 degrees Celsius to the object at 0 degrees Celsius until they reach the same temperature. Heat capacity. Heat capacity is represented by the symbol C. The heat, represented by the symbol Q, absorbed by a system and its corresponding temperature change, delta T, are directly proportional. The proportionality constant between Q and delta T is the system's heat capacity, again, which we represent as a C, a measure of the system's ability to absorb thermal energy without undergoing a large change in temperature. The formula that we use is Q equals C delta T, which can be represented to isolate the heat capacity by saying C is equal to Q over delta T, and we know that the unit for heat will be joules, and the change in temperature will be degrees Celsius. Could it be Kelvin? Of course it could be Kelvin, as long as you're consistent. The heat capacity of a system is the amount of heat required to raise its temperature by 1 Kelvin or 1 degree Celsius. A temperature change in Kelvin is equal in magnitude to a temperature change in degrees Celsius, as 1 Kelvin is equal to 1 degree Celsius. And this is a really important point, so I'm going to put a little star by that because, yeah, you got to know that one. The greater the heat capacity of a substance, the greater the heat required to produce a given increase in temperature. Heat capacity is an extensive property, so heat capacity depends on the amount of matter being heated. Specific heat capacity is also known as, well, just specific heat. Specific heat is defined as the amount of heat required to raise the temperature of 1 gram of a substance by 1 Kelvin or 1 degree Celsius. Specific heat capacity is represented by the symbol little c. A lowercase c is used when dealing with mass. The value for specific heat capacity varies with the substance. So the specific heat capacity of water is really, really high, 4.18 joules per gram degree Celsius, and the specific heat for something like mercury is really, really low, 0.14 joules per gram degree Celsius. So specific heat really depends on the substance that you're using. An expression involving heat, mass, specific heat capacity, and change in temperature can be represented by the formula Q equals mc delta T, where Q is the quantity of heat transferred, measured in joules, m is the mass of the substance, of course, measured in grams, and the little c here is the specific heat capacity in terms of the mass of the object that you are examining. So specific heat capacity will either be measured in joules per gram Kelvin or joules per gram degree Celsius. Your delta T is your change in temperature, measured in either Kelvin or degrees Celsius. Just make sure that you're consistent. Delta T is always temperature final minus temperature initial. If your delta T is a positive value, the temperature of the system increases. This is an endothermic reaction, and it's endothermic because energy is absorbed by the system from the surroundings. Now, people get really confused by this because they're like, wait, energy is being absorbed. Shouldn't the temperature be going up? No, because we're not measuring the system. We can only measure the surroundings. And if energy is being sucked out of the surroundings, the temperature is going to decrease. So, the overall temperature of the surroundings must decrease, look, I just said that, due to the transfer of thermal energy to the system. So the system is taking in the energy is being removed from the surroundings, therefore you're going to see a drop in temperature. If your delta T is a negative value, the temperature of the system decreases. It's an exothermic reaction. Energy is being released. Energy is being released by the system to the surroundings. Thus, the overall temperature of the surroundings must increase, which we can measure, due to the transfer of thermal energy to the surroundings. Molar heat capacity. Molar heat capacity is defined as the amount of heat required to raise 1 mole of a substance by 1 Kelvin or 1 degree Celsius. It's represented by the symbol capital C and then a little subscripted molar. The unit of molar heat capacity is joules per mole degree Celsius or joules per mole Kelvin. Specific and molar heat capacity example problems. The temperature of 50 grams of water increases by 1 Kelvin when 209 joules of thermal energy is absorbed from the surroundings. Calculate the specific heat capacity for this sample of water. So what are we given here? We are given a mass. We are given a change in temperature. It's just telling us we're increasing by 1 Kelvin. So that's our delta T. We're given an amount of thermal energy. So this must be our Q. And we're trying to calculate the specific heat capacity. So the formula that we're going to use here is Q equals mc delta T. Now you could just take those values and plug it in and solve for the variable. And of course the variable that we're solving for is C. Or you can rearrange the formula right here to isolate C by itself to hopefully make things a little bit easier. So if I isolate C, my formula will be C equals Q divided by mass times change in temperature. And if I plug those things in, C is equal to 209 joules divided by the mass, which is 50 grams, multiplied by the change in temperature, which is 1 Kelvin. And if I do all the math here, I should get a specific heat capacity of 4.18 joules per grams Kelvin, which is what I want in terms of my units for specific heat capacity. Let's do another example. 175 grams of a metal absorbs 122.5 joules of thermal energy. The temperature of this sample increases from 32 degrees Celsius to 37 degrees Celsius. Determine the specific heat capacity for this metal. So let's see, what do I have here? I have a mass, I have a Q, and then I have a temperature initial and a temperature final. So by taking the difference between those two, I can get my delta T. So really what I need is my C. The first thing I am always going to do is write my formula. So Q equals mc delta T. Again, like the previous problem, I'm going to isolate my specific heat capacity. So when I set this up, C is equal to Q over m delta T. Now before I go and I plug all my variables in and everything, I'm going to look at this delta T. I can calculate that really, really quick. So temperature final minus temperature initial. Temperature final is 37 degrees Celsius minus 32 degrees Celsius. So if I take the difference there, I get 5 degrees Celsius. Excellent. Now what I'm going to do is plug all of my other variables in. So C is equal to the amount of thermal energy 122.5 joules divided by the mass, which is 175 grams, times that delta T, which is 5 degrees Celsius. So if I work out my calculations, I should get a final answer of 0.14 joules per gram degrees Celsius. Let's look at another example. Determine the molar heat capacity. So we're doing something a little bit different here. For 1 mole sample of mercury, the specific heat capacity of mercury is 0.14 joules per gram degrees Celsius. Okay, so the first thing that we're going to do is write down our given. 0.14 joules per 1 gram times 1 degree Celsius. That's a degree symbol. Okay, now I'm in grams. This is representing 1 gram of mercury. I want to be in moles. So like any dimensional analysis problem, I'm going to put a multiplication sign and a line. I want to get rid of the unit of grams. So if grams is on the bottom, I need to put grams on top. Grams of Hg. I want 1 mole. And I know that the atomic mass of mercury is 200 per 1 mole of mercury. So by doing this, I can now look and cancel units. So 1 gram is canceling my grams. And if I work out the calculations, I will have moles on the bottom, which is what I want. So if I multiply together 0.14 times 200, I will get 28 joules per 1 mole now degree Celsius. So that's how you convert from specific heat capacity in 1 gram to molar heat capacity. Let's do one more example. A final temperature of 130 degrees Celsius is recorded after 2,520 joules of heat energy is added to a 200 gram sample of mercury. Calculate the initial temperature of this sample. The specific heat capacity of mercury is 0.14 joules per gram degrees Celsius. So again, I'm always going to look at the variables that are given to me. I have a final temperature of 130 degrees Celsius. So this is my T final. I have a Q right here of 2,520 joules. I have a mass of 200 grams. And I also have a specific heat capacity, little c, right here. Given all of that information, I know that I'm going to use the formula Q equals mc delta T. Now, what is different about this problem, I am solving for the initial temperature. So remember, your delta T here is calculated by taking temperature final minus temperature initial. So I'm going to rewrite this problem out again. Mass, specific heat capacity, temperature final minus temperature initial. To make things easier for you, think of this temperature initial as X. All we are doing here is solving for X. So the Q that is given to me here is 2,520 joules. The mass is 200 grams. My specific heat capacity is 0.14 joules per grams degree Celsius. Okay, that whole thing right there. Excellent. Now, temperature final minus temperature initial. My final temperature is 130 degrees Celsius minus X. X is my initial temperature and what I'm solving for. What I am going to do here is the distributive property. So 2,520 is equal to 200 times 0.14 times 130. So all three of these things multiplied together is going to give me one number. Then, because I am distributing these two numbers all the way through, it's going to be 200 times 0.14 times x. Now when I do this and I multiply these things together, 200 times 0.14 times 130 gives me 3,640 minus, now multiply 200 times 0.14. And when I do that, I get 28x. And of course, this all is equal to 2,520. Now, I need to swing, because I'm trying to get the x by itself, I need to move the 3,640 over to the other side. So minus 3,640, so that cancels itself out, minus 3,640. The difference here is negative 1120 is equal to, hey, there's a negative in front of there, negative 28x. I divide both sides by 28, negative 28, of course. Negative divided by a negative is a positive. I have solved for x. X, which is equal to my temperature initial, is equal to 40 degrees Celsius. And if I plug the 40 degrees Celsius back into up here, actually right up here, these two values will be equal to each other. Now, of course, there are multiple different ways that you could do this, but in terms of the most straightforward way possible, think about plugging the values in and doing the distributive property. Just watch your negative signs. So what did you learn? We went over the concepts of heat, temperature, and thermal equilibrium. We talked about heat capacity, specific heat capacity, and molar heat capacity. And then finally, we did some specific and molar heat capacity example problems. Need more help? Feel free to contact me. Have a great day.